Hey, good morning. We have homework, our last homework assignment due this Friday. It's over chapter 10, and I wanted to know if anybody had any questions about it. All right, well, you can bring your questions on Wednesday, so try to get an early start on it and bring the questions so that we can clear up any that we have. Now, we're going to continue chapter 10 today, and today is really the last new material we'll cover in the semester, because on Wednesday and Friday we're going to be reviewing for the final exam, which is a week from today. In fact, 1 week from right now you'll be starting the final exam right here this time. So let us finish up chapter 10, and we were talking about feedback, and remember we're going to continue on feedback, and we're going to look a little bit at some of the control problems that can happen with feedback. Some of the engineering students might have seen this in like a control theory course, but we're going to look at what can go wrong with feedback. So I want to look at problem 22 from chapter 10. So it says, consider two substances in the plasma with concentrations capital X and capital Y. They might be glucose and insulin. Assume that the experiment has established the following facts. So, we're going to assume, first of all, that we figured out what the set point is. Last class we talked about how finding the set point. We're going to say that the set point is x0, y0. So those are the two values. And then we're going to measure deviations from the set point. So we're going to find little x to be capital X minus x0 and little y to be capital Y minus y0. Now, why do that? Well, sometimes in these feedback problems, the relationships between capital X and capital Y can be very complicated and nonlinear. But if you have a couple of curves where, say, this is big X and big Y, and maybe one goes up like this, and maybe one comes down like this, and this is your set point. If you look at just a small area around the set point, it's going to be approximately linear around that set point. So what we're going to do is we're going to end up making sort of a linear approximation of the feedback system. We're going to be able to learn what happens with small deviations away from the set point. So the first thing another thing the problem says is the steady state values, okay, we did that. When y is equal to 0, x is removed from the body at a rate proportional to x. So, a rate proportional to x, that means you expect some sort of derivative is going to be proportional to x, and it's removed, so it's minus. So we can say it's x, and we'll call this proportionality constant tau 1, because it's sort of like a time constant. So we know that it has this behavior when y is equal to 0, little y's. But when x is equal to 0, y influences the rate at x changes in an approximately linear fashion. An increase of y above y0 increases the rate of disappearance of x. So if you've got y increasing the rate of disappearance, what you do is you pick up another term, and it's going to be proportional to y, so you're going to get a times y. So now your equation looks like this. And now there's another equation for y, and that equation says when x is 0, y is clear to the rate proportional to y. So again, you get the exponential decay, and the rate dy dt is proportional to y. It's cleared, meaning it removes it, so it's minus. And oops, this is now a different time constant, tau t. So it doesn't have to have the same time constant as x. And finally, when y is 0, so if y is 0 and x is non-zero, a positive value of x stimulates the production of y. So a positive value of x stimulates, so a positive x will make more y, so you're going to get a plus sign, and you're going to get another proportionality constant, bx. So if you're assuming a linear model around a linear approximation, this is about as general of a relationship as you can get. Now, what did we do when we were looking at feedback systems? Well, first thing, we usually looked at the steady state case. Steady state means time derivatives are 0. So if we put the time derivative to 0 here, we'll get minus x over tau 1 minus ay is equal to 0. And we can solve this, and I solved it for x. And you'll get, in steady state, x, and you'll move the tau 1 over, and you'll still have a minus sign, a tau 1 y. So that's a steady state relationship. And you can also get a steady state relationship for this one, which you'll get y, solve that for y, is equal to, now it's going to be plus tau 2 bx. B tau 2 x. And it's kind of important to get the causality right. This is really our equation describing x, and that's why we described this one for x in terms of y. This is really our equation describing y, so we solve it for y. Now, we said that we like to draw feedback loops in this little generic way, so let me draw this. This is x as a function of y. So y, and it'll give us the value of x. And this is going to be a negative slope, and it's just a lit line going through the origin. This says, if you tell me y, I'll tell you x. So it spits out a value of x, and now here, this equation says, if you tell me x, I'll tell you y, and this also has a slope, but it's a plus slope by design. So it looks something like this. And out comes y, and this feeds back over into here. And you got some parameters, a, b, tau 1, tau 2 are all parameters that can go into this problem. So it's not too surprising that the set point's obviously going to be 0, 0, because that's how we defined it. So this is the way the feedback loop looks. The main difference between this example and the one we did in class on a week ago Monday was that both of these have time dependence, have a dx dt and a dy dt term. In class, when we looked at, I believe it was carbon dioxide and breathing, we found that one of them we assumed had time dependence, the other one was instantaneous. Okay, what do we want to do now is we want to put these two together. So really, we're going on to the next problem. We've solved problem 22, and now problem 23 says, combine the two equations obtained in the previous problem into a single differential equation in x. And then it says, show it has a certain form. So let's try to do that. We want to put these expressions together. So what we're going to do is we're going to start off, we're going to take the derivative of this, time derivative. So we'll have a second derivative. Equals minus, and now we'll have 1 over tau 1 dx dt minus a dy dt. Not exactly obvious why we did that to start off with, but now we can say, aha, I know what dy dt is. It's just this. So I'll plug that in for dy dt. So what we now have is d squared x dt squared equals minus 1 over tau 1 dx dt. And now we have a minus a times dy dt. So minus a times this becomes plus a over tau 2y. And then we have a minus a times this term. So minus a dx. We almost have this just in terms of x, but we've still got this y in here. So how are we going to get rid of the y? Well, this equation has a y and an x and a dx dt. We can just solve this for y and plug it in. So I'll do that. I'll solve this equation first of all for y. And I get y is equal to minus x over a tau 1 minus 1 over a dx dt. That's just this, solved for y. And I'll take this and I'll substitute it in the y. So we're almost there. We get d squared x dt squared equals, you get a minus 1 over tau 1 dx dt. You get now a plus a over tau 2 times y. So that's a over tau 2 times these things. So that's a plus, but there's a minus sign. So minus a cancels that a. You get a tau 1 and a tau 2. So you're going to get a x over tau 1, tau 2. And in this term, it had a plus, but there's a minus. The a's cancel again. So you're going to get a plus minus, there's the minus 1 over tau 2, 2, dx dt. And there's finally this term, minus abx. Okay, we're almost there for the equation. What we can do is we can just move everything, we can move everything to the left, and we can say d squared x dt squared. Now we have two terms with dx dt. This one has a 1 over tau 1, this one has a 1 over tau 2. We're going to move to the other side so the minuses become plus. So we get plus 1 over tau 1 plus 1 over tau 2 dx dt. And then we have two terms that are proportional to x. We have this term and this term. We're both negative, but we're going to move to the other side, so they become plus. What I want to do is I want to put it all over tau 1, tau 2. So this term here didn't have a tau 1, tau 2, so I have to put it upstairs. AB tau 1, tau 2. And this term here has the tau 1 and tau 2, so I just get plus 1. And that, all times x, is equal to 0. Okay. So I'm going to put a box around that. We worked hard to get that equation. We've solved this. These types of equations you've probably seen before. For instance, if you're solving a spring, mass on a spring with friction, this would be like the F equals ma term. This would be like an acceleration. This would be like the frictional term, and this would be like the spring constant term. It's a linear second-order differential equation. We can kind of recognize this AB tau 1, tau 2. Ought not to be too unfamiliar, because last class, remember we talked about open loop gain? And we defined the open loop gain to be the x dy times dy dx. It's really the slope of these two curves. But you have to be a little careful. This refers to the steady state solution for x in terms of y, and the second one, dy dx, takes this equation, which gave you y if you give it x. So this was just the x dy would be minus a tau 1. The y dx is plus b tau 2. So really, this AB tau 1, tau 2 is just minus the open loop gain. So we could have written that as minus open loop gain. We could have written it as 1 minus the open loop gain. So it's not too surprising the open loop gain comes into this problem. All right, now, how does one solve a differential equation like this? You need some function that looks like its first derivative and looks like its second derivative. Now you might say, well, maybe it's a sine or cosine. Well, that would work for a function that looks like its second derivative, but it doesn't really look like its first derivative because the sine would turn into the cosine. Let's try an exponential. So I'm going to have to get some more space here before I start erasing things. Are there any questions to this point to get this equation? And okay, I'm going to erase everything except the equation in the box. Let us guess. My favorite method for solving a differential equation. I'm going to guess and check. So I'm going to guess this solution. X is equal to e to some constant little a times time. So it's an exponential behavior. I have to plug in the time derivative. So what's the time derivative of x? What is dx dt? Somebody help me out. What's dx dt? What is it? It's a from the chain rule, and the derivative of exponential is still the exponential. So you just get a times e to the at. So this is kind of like if you've seen, what is it called? Not Fourier transforms, but Laplace transforms. It's kind of the same thing, except we're using a positive exponential, but a can turn out to be negative, we'll see. And the second derivative is just, you're going to do the same thing. You're going to get another factor of a comes down, so you have a squared, e to the at. And now we're going to plug all these into our differential equation. So here we're going to get, every term is going to have an exponential. So I'm going to just cancel them out right from the get-go. I'll get a squared here for the second derivative because of this a squared. I will get a plus 1 over tau 1 plus 1 over tau 2 times the x dt, which is just going to give me an a, and I canceled out the exponential. And I'll get a plus big A, big B, tau 1, tau 2, plus 1 over tau 1, tau 2, and then I'll get just the exponential. So it's already canceled out. So all that gives 0. So that's all an expression for A. Now that's just a quadratic equation. So we know how to solve quadratic equations. So this is going to be A equals plus or minus. Well, this would be the linear term. So it'd be, if this was a squared plus bx, ax squared plus bx plus c, this would be like the b. So plus or minus 1 over tau 1 plus 1 over tau 2. No, it wouldn't need to be that. It would be minus that. Plus or minus, what? The square root of this thing squared. 1 over tau 1 plus 1 over tau 2 squared minus 4 times the coefficient here, which is 1, times this coefficient. So minus 4 times AB tau 1 tau 2 plus 1 over tau 1. All over 2 times 1, all over 2. Alrighty. We can simplify this slightly. A lot of these terms have this factor in front of it. This factor of minus 1 over tau 1 plus 1 over tau 2 all over 2. So let's factor that whole thing out. You just get a 1 out front. Now, we factored out the minus sign, so instead of plus or minus, we have a minus or plus. But that doesn't mean much. We factored the 2 out. We factored this. This was 1 over tau 1 plus 1 over tau 2 squared inside the radical. So you factor that out, and you just get a 1. Because you get the 1 over tau 1 plus 1 over tau 2. This is the complicated term. Minus 4 AB tau 1 tau 2 plus 1 over tau 1 tau 2 times, and now we factored out this thing. Under the radical it's squared, so I have to get a 1 over tau 1 plus 1 over tau 2 squared. That is how we get A. Okay. Now, here's the question. If A, well, first let's then analyze this. If A is real, then you're just going to get exponential behavior. In particular, if A is negative in the real, it just decays away exponentially. We've got a minus sign out here, so that sounds, it's likely that we can get something to be negative. But if A is imaginary, what happens? What is e to the I AT? How does that behave? Anybody know how e to the I? Well, there's a relationship, goes back to Leonard Euler. E to the I z is cosine z plus I sine z. So if we get this thing to be imaginary, then we're going to get an oscillating function of time. So now this brings up whole new possibilities. You can have just a simple feedback loop, and the response would be it's going to oscillate around its set point. Perhaps a decaying oscillation, or if it's pure imaginary, it'd be just an oscillation. You can sometimes imagine you had your furnace. That's the classic feedback loop. Imagine that your furnace turned on, your house starts heating up. And then your furnace got up to the point where it's supposed to, it gets hot enough, according to your setting, and it's not going to, but for some reason there's a little delay or something, the furnace kept going and get hotter and hotter until finally the furnace would shut off, and then your temperature would stop dropping, but it might overshoot and go down below where you want it until finally it causes the furnace to come on. And you can see that happening over and over again, an oscillation. It's very common in feedback loops. It's usually you don't want that. You don't want things oscillating around. You want to have just a nice flat set point. But you can get oscillations. So let's see under what conditions can you get oscillations. In order to have oscillations, this is the only place where you can get an imaginary number. This is a square root. If the square root is less than 1, the thing inside the square root is less than 0, then you can have square root of a negative number, and you can get these oscillations. So you can get imaginary coefficients. So it could be imaginary. So you get oscillations if 1 minus 4 AB tau 1 tau 2 plus 1 over tau 1 tau 2 1 over tau 1 plus 1 over tau 2 squared has to be less than 0. That way you can get oscillations. Now I'm going to try to simplify this a little bit. Be a little bit math, but we can come up with a slightly simpler way to express this condition. Okay, first of all, we're going to move this thing over to the other side, and then we'll swap places because that's just the way I did it in my notes. So you're going to get 4 AB tau 1 tau 2 plus 1 over tau 1 tau 2 times 1 over tau 1 plus 1 over tau 2 squared, and that has to be greater than 1 because we basically moved this to the other side and then we flipped it around. So you want this thing to be big. We can just multiply through. I hate having this thing in the denominator, so we'll multiply through by that. So multiply both sides by 1 over tau 1 plus tau 2 quantity squared. 4 AB tau 1 tau 2 plus 1 over tau 1 tau 2 has to be greater than 1 over tau 1 plus 1 over tau 2 squared. And this thing, we can actually expand this out. Doesn't seem like it's making life simpler, but it will in the end. 1 over tau 1 squared plus 1 over tau 2 squared plus 2 times tau 1 tau 2. And this side, we can make it to be 4 times AB, tau 1 tau 2's cancel, plus 4 1 over tau 1 tau 2. That's that term. Now, to make this simpler, I'm going to take the 4AB and leave it here. I'm going to subtract off 4 tau 1 tau 2 from both sides. So I'll get 1 over tau 1 squared plus 1 over tau 2 squared plus minus 2. I'll get 4 of those minus, bring it to the other side, I'll get 2 minus 4. So you get minus 2 tau 1 tau 2, which you can write as 1 over tau 1 minus 1 over tau 2 quantity squared. Just to check that. There's the 1 over tau 1 squared. You get a 1 over tau 2 squared. You get a minus 2 tau 1 tau 2. So that works. So finally, the condition is, I sort of lost my sign there. I think this one should have been a greater than sign because it was there. So you get 4AB has to be greater than 1 over tau 1 minus 1 over tau 2 squared. That's the condition to get oscillations in the feedback loop. So how can you get oscillations? Well, you've got a couple choices. You can have A and B, their product, be very big. And A and B is almost the open loop gain. AB times tau 1 tau 2 is the open loop gain. So basically, if you have a large open loop gain, you're going to be more susceptible to oscillations in your feedback loop. Also, if tau 1 was the same as tau 2, then you get 0 on this side, and you always have this condition fulfilled. So if you have a feedback system where the time constant in both parts of the feedback loop are almost the same, you're going to be very susceptible to oscillations. Last time we looked at feedback loops, we had one had a time constant and the other one was instantaneous. That would correspond to very different time constants of the two. One of them would be extremely short. So that would make it almost immune to any oscillations. But in general, if you have a large open loop gain or you have the time constants about the same, you're going to get this kind of behavior. You get oscillations plus some negative real parts, so it's going to be decaying oscillations. So your feedback loop is going to do something like this. It's going to oscillate a ring and slowly go down to your set point. Okay, if it turns out that you don't have any imaginary part, so if this turns out to be greater than 0, then you'll just get a decay down to 0, which is sort of what you want. So with feedback loops, you always have to be worrying about oscillations, and it can lead to some problems in the body if you get these oscillations. So, any questions about this analysis? I know there's a lot of math right into here, but at least it gives you some insight on how these oscillations can appear. Well, let me just give you some examples in words. Okay. Okay, well, first of all, have any of you ever gone to the swimming pool and jumped in under the water and tried to see how long you hold your breath? Okay, and or maybe you go 30 seconds or something, but then you start having an overwhelming desire to start breathing. And the reason isn't so much because your body needs oxygen. The reason is your lungs begin to fill up and your blood begins to fill up with carbon dioxide, and it can't get rid of the carbon dioxide. And there is a mechanism in your body that when carbon dioxide levels rise, it triggers increased breathing. So you'll blow off the carbon dioxide. If you're forcing, voluntarily suppressing that, you begin to get this overwhelming desire to breathe. So that sets up a feedback loop. So let me just show it in a picture. This is going to be the concentration or the of CO2, the partial pressure, if you want to use that term, of carbon dioxide, and this is going to be breathing rate. Now, if you breathe fast, you're going to be blowing out the carbon dioxide, and you're going to force the amount of carbon dioxide down. So that's following a function like this, and that's half of your feedback loop. And that tells you, if you tell me the breathing rate, I'll tell you the carbon dioxide level. But, like I said, your body has a mechanism that will detect carbon dioxide in your blood. And if it gets too high, your body will simply insist that you breathe more. So this is going to be breathing versus PCO2, and your body will increase the breathing rate as CO2 goes up. And that's the other part of the feedback loop. And this will give you a breathing rate, which will come around and come into here. So on normal conditions, we're breathing comfortably, and it's set by basically trying to maintain a carbon dioxide level that's a fairly low level. Doesn't have to be zero, but fairly low. All right. What happens if you start getting oscillations in this system? Well, there's a specific type of oscillations that can set up. It's called Cont-Stokes breathing. And what happens is something goes wrong with your feedback loop. Either your open loop gain somehow gets out of whack, or the time constants get out of whack. But you begin to have a situation where, first of all, you're breathing pretty fast. And it lowers your concentration of carbon dioxide. But it lowers it too much. It lowers it so low that it causes your breathing to slow down really slow, almost to stop. And then, if your breathing stops, your carbon dioxide starts going up. And next thing you know, you're breathing like this. Blow off all that carbon dioxide, and then you practically stop. And this can happen especially to people when they're at night, when they're asleep. So their breathing rate, if you plot their breathing rate, say breaths per minute versus time, they end up with this really kind of weird thing where they're going through these oscillations. This is not a horrible disease, but it's kind of a strange one where you can get these kind of weird behaviors, and it's known as Cont-Stokes breathing. It's an example of what's known as a dynamical disease. That is a disease that wasn't caused by a broken bone or a hormone that's out of whack. It's caused by a feedback system that's out of whack. So you can get examples of feedback systems out of whack. The book has some other examples. For instance, if you look in figure 10.35, you see a feedback loop that looks at white blood cell production, and you can get a feedback loop set. I won't go through all the details, where you can actually get oscillations. And if the deviations, remember when we looked at our model here, we were looking at small deviations from the set point, so you had a linear model. But if you get larger deviations from the set point, you can get these models to be nonlinear. And when they're nonlinear, opens up the possibility where you don't just get an oscillation, you can actually have chaotic responses. So you can have chaotic behavior that comes from a feedback system screwed up. So that really is the last thing I want to talk to you about with feedback systems, is the possibility of problems arising. So if anybody who's worked with feedback systems, say in a mechanical situation like in a car where you're trying to make an autonomous car and you're going to have to detect stuff through feedback, you always have to worry about oscillations and other problems arising in the feedback loops, and so too with the body. Okay, questions about feedback loops. Questions about the homework, and especially the first 4 problems, which are all about feedback. Or any, well, this marks the end of our new material, of our new material for the class. Everything else is going to be reviewed. So what I wanted to do in the last part of today is to just go over the topics that will be on exam 3. Remember, your final exam when you come in a week from today, it's going to be 2 parts. One I call exam 3, and it's over chapter 7, 8, and 10. And the other part is going to be the comprehensive part, which is just questions from the old exams and practice exams. So I want to focus right now on exam 3. So let's see what we got.
So is the exam 3 going to be just as long as exam 1 and 2?
Yeah, it'll be almost identical in format to exam 1 and exam 2, and for that matter, to the practice exams for exam 3, which I did send around. The comprehensive part will be very similar in format to the exam 1 and exam 2. I'll have about the same number of questions. So you have about twice as much exam to solve, but you'll have 3 times the time, because you'll have a full 3 hours. Okay, so let us see, first of all, chapter 7 was about extracellular potentials, about electrical potentials outside nerves and muscle. So the first thing we talked about is stimulating nerves. And we imagined you had an electrode outside the nerve axon, and we tried to figure out how you'd stimulate it, where it would be stimulated. And then we developed something called activating function. So that could be on the exam. I could give you electric potential distribution outside the axon and a certain distribution, ask you to calculate where it would stimulate if it was a cathode versus an anode. So we're basically talking about stimulation, electrical stimulation. Some of the applications were to neural stimulation, like in a cochlear implant in the ear, or neural stimulation to try to restore walking, those kind of things. And then we went on and we looked at what extracellular potentials are produced by nerve axons. And we looked at the extracellular potential outside a nerve axon. And we developed some equations for it. We did some analysis of how you calculate it. So that was going to be extracellular potential. I'll make these bullet points. Extra. And then we derived the case of what the extracellular potential would look like if you were a long ways away from the nerve axon or the cardiac muscle or whatever. So you're a long ways away. We made some approximations and we got the dipole approximation. So you want to understand what the dipole approximation is and remember how that works. And then we started looking at this, a lot of examples with the heart. So we started looking at the heart, and the first thing we did is we had to learn some of the heart anatomy. So we took the heart and we learned its anatomy, which included the major vessels, included the major chambers and where they pump to, and included some of the valves, and especially it included the conduction system that related like the SA node and the AV node. And then we looked at the electrocardiogram, or EKG, which is an example of extracellular potential produced by dipole. And we did all trying to diagnose what different electrocardiograms meant. And then how do we treat these problems that can arise in cardiac systems? We looked at pacemakers and defibrillators. And that really was chapter 7. We may have discussed a few other things, but those are the major concepts. And if you look on the practice exams, those are the major things we talked about, or questions from the practice exam on those. Notice I'm not writing down a lot of equations. For the equations you have to know, and that's because basically I'm going to give you the equations. If I ask you to calculate the activating function for a nerve, I will remind you that the activating function is actually the second derivative of the extracellular potential. I will tell you that the extracellular potential of a point electrode is I, the current, over 4 pi conductivity times R. But you have to know how to use them and what to do with them. Okay, so but not a lot of equations to memorize this time. Then we go on to chapter 8. Okay. We looked at biomagnetism. We looked at magnetic fields produced by nerves and muscle. We found 2 ways to calculate magnetic fields. One was through the law of Biot and Savart, but it was kind of complicated with this cross product thing, so I told you it wouldn't be on the exam, so it won't be. So you won't have to do the law of Biot and Savart on the exam. But the other one was Ampere's law. So biomagnetism from Ampere's law. And that one could be on the exam. And remember, that is when you have, you make a little loop, and you integrate the magnetic field around the loop, so you basically get the magnetic field times 2 pi r, the loop, the circular loop, is equal to the mu naught times the current enclosed within that loop. And we did the example where you had intracellular currents plus some fraction of the extracellular currents. You'll see that a problem like that in the practice exams. You need to understand the Ampere's law calculation.
So the electric, so the EEG isn't going to be on the exam?
EEG is not going to be on the exam. Yeah, I wanted to try to get the things that would be on the exam somewhat reduced so you know specifically what to study. So the electroencephalogram won't be on the exam. Okay. Well, almost true, because when we talked about biomagnetism, we also talked about the magnetoencephalogram, the MEG, and we compared that a little to the electroencephalogram. So I do want you to know enough about the electroencephalogram to be able to qualitatively compare it to the MEG. We said things like you had to put electrodes on the head with the electroencephalogram, but the magnetoencephalogram, you just put a big helmet, there's no contact. We said things like the MEG tends to be really expensive, the EEG tends to be cheap. And we even compared these to other systems like functional magnetic stimulation and positron emission tomography. You don't need to know those techniques in any detail, but you should have some idea on the relative advantages and disadvantages of these methods. But there won't be a calculation where I make you calculate the EEG. So in that sense, it won't be on the exam. And finally, we looked at Faraday's law of induction, which led us to study magnetic stimulation. And one thing we looked at in kind of detail is we derived the cable equation, but we added a term for magnetic stimulation, and we ended up getting something that looked a lot like the activating function, but for magnetic stimulation. Instead of the second derivative of the extracellular potential, we got the first derivative of the electric field along the axon. And then we analyzed some problems where you had to, if I gave you the electric field induced during magnetic stimulation, you had to figure out where it would be stimulated and where it would not, and if you change the polarity, where it would be stimulated and what kind of delay that would introduce in the propagation of the action potential. That is a question that's on the practice exam and that you should be able to handle. So a little bit about what magnetic stimulation is, and in particular trying to calculate where magnetic stimulation occurs is something that could easily appear on the exam. Then we skip chapter 9. So we go to chapter 10. And we spent a whole day talking about restitution and chaos. Restitution. Restitution is when action potential duration depends on how much time you had since the last stimulus, since the last action potential. So if you had a long time between the last action potential and then you stimulate, you get a very long action potential. If you had a very short time, you get a short action potential. And we developed a simple model for that. We looked at how you can get normal behavior if you stimulate slowly, stimulate more quickly. You can get these things called alternans, which would be a long action potential, short action potential, long action potential, short action potential. You can get 2-to-1 behavior because you're still refractory when you have your stimulus every other time. So you fire, and then you're refractory on the next stimulus, and then you finally recover, and then you fire, and then you're refractory on the next stimulus, 2-to-1. And you can, even if you stimulate fast enough, you get chaotic behavior. And we saw how this chaotic behavior depends in part on the slope of the action potential restitution curve. That is, how the action potential duration depends on what's called the diastolic interval, the time between the end of the last action potential and the stimulus. And it was something like this. And if the slope gets too high, it throws you into more of this chaotic behavior. So you ought to be comfortable, if I gave you an example, like I did on the practice exams, of restitution and chaos. You want to be able to analyze that. Then we had fun and games one class where we gave you all those hexagon things, and we had that 3-state cellular autonoma. So it was a cellular which is a fancy name for that hexagon game, where you had 3 states. In our example in class, at least, there was 3 states: quiescent or resting, excited, and then refractory. And we just had that game explaining how you step the states forward. And we found that even though it was a really simple kiddie game, you can actually learn about spiral waves and phase singularities, and all kinds of interesting behavior could be described. And you'll see in one of the practice exams, there's an example of a cellular automata with a slight new twist, so it's not exactly the same as what we did in class. Those could be on the final. And then we spent the last few days talking about feedback loops. And we probably won't be talking in any quantitative way about oscillations, but we certainly could give you quantitative problems about a feedback loop like you did in your homework. First 4 problems in your homework, like here's one of the problems in the practice exam. I give you, sort of in words or equations, the relationships between some variables. You have to draw a picture of the feedback loop, find the set point, maybe find a new time constant with or without feedback, change some parameter and find how the set point changes. Those kind of things with feedback are important. So really, it's in a sense 9 topics, 3 from each chapter, that are going to be covered on the exam. And so that's what you need to know. And like I said, if I have an Ampere's law question, I'll give you Ampere's law. If I have an activating function question, I'll give you what the activating function is. I'll give you any information you need for feedback. So what you need to do is you need to understand them and know how to analyze them. So all we really have left to do is go over those practice exams, which I have sent to you. And that's what we'll spend all day Wednesday and Friday doing, is we will go over practice exams 3A, 3B, and 3C. And hopefully you've come to realize that those practice sessions before the exams aren't just sort of things you should skip. They are really important to being able to do well on your exam. So I strongly encourage you to come. And the best thing you can do is you can spend some time solving these practice exams now, and then that way when you come to class, you can just sort of fill in any questions you have and really be prepared to be able to do well. Okay, last chance. Anybody have any questions on the homework that is due on Friday, or anything else about the exam? You will have to know the equations that were required for exams 1 and 2. So it's not like you don't have to memorize any equations. You still have to know what those equations are, but you know exactly the questions that will come. And if they weren't in any of the questions, you don't have to memorize it. If they were, you just still have to apply to those. In that case, I will see you on Wednesday, and we will start going over the practice exam.